Welcome everybody on Zoom in the lecture hall from the future. Today we are going to continue the lecture on HDFS, these distributed file systems, and then we will move on to syntax, because after we have seen how to store files, we need to see what there is in the files. So before we start, as always, I'd like to ask you a question. It's kind of a guess, because of course I barely started last time to tell you what there is inside. So this is almost looking into what we will do today, but let me still see. So the clients that connect to HDFS, so these are the ones that store the files there. With which servers do you think the client must communicate to create a directory in HDFS? We saw it's a hierarchy of files and directories. And what about blocks, to get the blocks for a file? Is it everything with the name nodes, or everything with the data nodes? Or is it with the data node for creating the directory and with the name nodes to get the blocks? Or is it with the name node for creating the directory and with the data nodes to get the blocks? Right, 26 answers, giving you a bit of time to wake up. It's only 8 a.m. All right, so I assume all of those who wanted to cast a vote did. About half of you, maybe. I think there's in total 60 people also on Zoom. All right, and the majority is, what do you think? Correct. So I will now get into the details of that and explain everything. So indeed, the name node, do you remember? It's a centralized system. The primary node, that's called the name node, and all the secondary nodes, they are called the data nodes. And this is where the blocks are. But let me get back to the slides. And let's take it from where we stopped last time. You might remember that I tried to structure the lectures into two steps. The first step is the logical data model, the logical level, and only then do I explain how this all works. The logical level of HDFS, as we saw, looks like this. So we have this hierarchy of files and directories. This is pretty much the same as you have on your laptop, so assuming you all know that. And the ones, so the directories can have child nodes, right? That can be recursively other directories, or that can be files. And then the files, of course, don't have any children, right? These are called the leaves by computer scientists. And then every file is associated with a sequence of blocks. And we saw that the size of the blocks, it's roughly 128 megabytes, right? You remember that? 128 megabytes every time we have a block, right? And so it can be gigabytes or terabytes in total. I insist that it's only the files that are mapped to blocks, right? For the directories, it wouldn't make sense because the directories are only containers. They are only for the hierarchical structure. So we have the blocks. And then this is where I finished last time. I told you that the physical implementation of HDFS is based on a centralized architecture where we have the name node that is on the top, that is doing the whole coordination. And then we have the data nodes that are below that are actually storing the blocks. We have a bit of a light problem. Yeah. Somehow I'm trying to figure it out with the sunlight, how to best organize this, but hopefully the light will be okay. All right, so we have the name node and we have the data nodes, and you can see the blocks, they are there. So there's no block in there at all. They are all on the data nodes. Now, let's take a file that some user decides to store in HDFS. So they will upload it. I will show you how a bit later. There's a command for that. You can just copy a file from your laptop to HDFS. And what happens is that the file can be large, right? It can be gigabytes of data. So what do we do first? Well, we divide it into chunks. So we divide it into chunks, and as we saw, this is the order of magnitude, 128 megabytes, and we just cut it. We don't care about the content of the file. We just look at the bits, the zeros and ones, and every time we find 128 megabytes, we just cut it into chunks. All right? I insist that here you must know the order of magnitude, right? On some systems like Google did it with 64 megabytes, and now the newer systems, they tend to increase that a bit because the hardware is evolving. And so now I think Azure now is going towards sizes of 4 gigabytes for chunks, right? Which is roughly 10 times more, right? But it's still the same order of magnitudes. This is the most important part. All right, so we divide it into chunks. What happens next? That's new. We replicate the blocks. It means that each one of these blocks, let's take this one, for example, is replicated. We have 3 replicas by default, and we store 3 copies. One here on that data node here, a second one there, and a third one there. 3 replicas. None of them is above the others, right? These are just 3 replicas. There is no such thing as a primary replica and secondary replicas. No, there's just 3 copies of that block that we call 3 replicas. I'll explain later how we choose the data nodes to store it on, but basically it's just spread all over the cluster. All right, so that's pretty much it, right? And the replication is for fault tolerance. Imagine that one of the data nodes crashes and we lose everything that there is on it. It's no big deal, we have 2 more copies, right? So this is how the entire system is built. We just make copies. It's just like a permanent backup of the entire system. All right, now what you need to be aware of is that the primary way to access HDFS, if you connect to it, is first via the name node, and it can be multiple people accessing it, multiple clients, right? Client is the name that computer scientists use when you connect to a server. You're basically a client. If you connect to a website, your browser is a client of the web server, right? So these are all the clients that use HDFS. Maybe these are people who would like to copy files over to use Spark or MapReduce that we will see later, right? We just don't know. They connect to the name node, and then they will connect to the data nodes for the blocks, as we will see. The entire implementation of Hadoop, so this includes HDFS, this includes also MapReduce that we will see later, and HBase that we will also see later. It's all in Java, right? Everything is in Java. So a lot of people like, for this reason, to also use the Java API to connect to HDFS, right? But fortunately, you can also easily connect via the command line with similar commands, as we will see, to what you have on your laptop. So you are not forced to use Java if you don't want to. All right. So now let's dive a bit deeper. Let's look into the name nodes, and then we'll look at the data nodes. But let's start with the name node. So if we look at what there is inside, it's basically the brain of the HDFS, right? So on the data nodes, there's just blocks. Since the data model tells you that files are sequences of blocks, you have to keep track of what blocks belong to what file, right? Because if you just look here, how can you know? Maybe there's 1,000 files with blocks all over the place. You just don't know. And it's the job of the name node to keep track of that. So the name node has 3 things to keep track of, 3 things. The first one is that it knows about the entire hierarchy of directories and files. There is a name for that. We call it the file namespace, right? That's just the directories and files. So you have a copy on the name node of the entire hierarchy of directories and files, so the names of the directories, the names of the files, but not the actual data, not the actual content of the file, just the names. And I put plus access control because you know that when you have files that you share with other people, you can set up ways to prevent other people from accessing your files, right? So you have a username, then the files are associated with your username. Maybe you have a group, and only people from that group are allowed to access that file. HDFS can do that. You can tell HDFS, just like on your laptop or on servers, this is the owner of this file, this is the group that file belongs to. Please make sure that only allowed people can access. And then you can choose, okay, I allow these people to read, I allow these people to write, I allow these people to execute, and so on. So this is what's called access control. This is not specific to HDFS. This is just a standard called POSIX that you also have on Linux and Unix file systems, and also Mac OS. And Windows, actually, because now I think that Windows also runs some sort of Linux kernel. Anyway, this is just the hierarchy of files and directories that is called the file namespace. That's just fancy word. Second, you need to know for every file what blocks it is made of. So you need a sequence of block identifiers, not the block themselves, of course, because that wouldn't fit on a single machine, right? This is just the name node here. So the data is on the data nodes on other servers, but on the data node, you have identifiers for each block. It's just like an integer. Let's consider it an integer for now. So it's basically a sequence of integers. So for example, dear file 1, maybe it's going to tell you that's the sequence of 2 blocks. So I mark them as green and blue. But in fact, that might tell you, okay, this is block number 1034, and this is block number 2003, right? For example. So you keep track for every file, every path, every file, you keep track of the sequence of blocks through their identifiers. That's called the file to block mapping. For whom is that clear? All right, so it's just a sequence of integers, and the integers identify the blocks. There is a third thing that the name node has to keep track of. It has to keep track of where the blocks are. Because here you just have the IDs of the block, but you don't know on which data node they are, right? So you have a third component of the name node that tells you that this block right here, this block is on that data node and on that data node. Of course, here I only picked 2, right? In reality, it's like more like 100 or 1,000, right? But just so you see, you just have the pointers to the data nodes. What is meant with this? Well, that's just the IP address of the data nodes or the host name of the data nodes, right? You know what an IP address is, right? On the internet. It's these integers that identify your machine connected to the internet. So this is exactly in that way that basically for every block, you have the host names or the IP addresses of the data nodes that are the other computers that you store it on. So this one is only stored here. That's actually problematic because it should be 3, right? But again, that's just for an example, and so on. For whom is that clear? 3 components. The entire hierarchy of directories and files together with access control, the mapping for every file to the sequence of block identifiers that are integers, and then a mapping from the block identifiers to the addresses of the data nodes that have them. The job of the name node is to make sure to keep track of that. It's its job, right? And when you modify, you upload files, you modify and so on, the name node has to keep track of all of that and update accordingly all of what there is in there. Now, normally, if I give you this, a specific snapshot of HDFS with this structure, plus the blocks that are on the data nodes, you can reconstruct the files. Who could reconstruct the files in that way? Right? Almost many of you, right? Just look up the file in the hierarchy, take the sequence of IDs, look up the addresses, and then go to the data nodes, take the blocks, and then you concatenate them in the order in which they appear in the file to block mapping. Okay. So that takes care of the name node, and I'll come back to it for efficiency and so on. But let's now go to the data nodes. So data nodes, well, it's boring. This is much more boring actually than what there is in the name node, but basically in the data node, there's just blocks. So here I put plenty of them. I think you can compute roughly the number of blocks you can have on a machine, right? Because if you consider, let's take a hard drive of 1 terabyte, for example, how many times can you fit 128 megabytes? Well, you can fit 8 times 128 megabytes in a gigabyte, and you can fit 1,000 gigabytes in a terabyte. So it's more or less like 8,000, right? So typically the order of magnitudes of the number of actual blocks you're going to have on a data node is 8,000, 10,000, this order of magnitudes. All right, it's just a division. So right, this is what there is. And in the end, this is stored on the local disk of the data node, right? Because remember, a data node is a computer. A computer has memory, a CPU, a hard drive, and so on, right? So in the end, all of these blocks, they are stored on the local disk, right? And if you actually would connect to the machine, you can actually do that. If you create an HDFS cluster on Azure or AWS, you can actually connect to the machine directly, bypassing HDFS, just forcing yourself into the system on the shell. And then you look at the local disk, right? You ignore HDFS, just look at the local disk. You will find plenty of files in the sense of the local file system, the local disk, of 128 megabytes in size. These are the blocks of HDFS, right? Okay, so we store the blocks on the local disk of every data node. Now, the data node has another job. So its first job is to store the blocks, the actual data, the actual content of the blocks, the bits. But its other job is also to detect when something's wrong. So the data node, if it notices that the disk has issues or crashes, that something is wrong, then it will report it to the name node. Even worse than that, it could completely crash. The data node can completely crash, but then the name node will notice, because we will see that it periodically checks if they are still alive. All right, but basically, since the data node has its own local hard drive, it's super easy to detect if there is a disk failure and take it from there. All right. Now, again, a few words on block IDs. This is a block ID, so I colored it like there. Of course, this is random, right? But so there is a block here, and its block ID is 7586700 and so on, right? So it's a very big integer, obviously. It's actually an integer that's called a 64-bit integer. It's called a long in some programming languages. Who heard of longs? Right. This is basically an integer that fits on 64 bits. It basically means that it can be up to 16 quintillion. Basically, it's an integer between 1 and 16 quintillion. That's a lot of space to store integers. Okay, so this is the integer ID. And so when I showed you the block mappings right there, these are actually these longs, these 64-bit integers. Okay. And something that I'm keeping for later, but I just mentioned it en passant, but don't worry too much about that, is that it is also possible when you connect to a data node to not get an entire block, but to get some part of the block. So you can actually request just from this position to that position, less than the 128 megabytes. This is something that will be useful for MapReduce and that I will come back to in a few weeks to explain why this is useful. But make no mistake, this is not random access, because you might be tempted to say, okay, but now if I can access actually just a few bits in a block, then I have random access, right? I can just access whenever I want, wherever I want in HDFS. Yes, but if you try that, it's going to be awfully slow. It's not meant to be used in that way. HDFS is meant to scan massively the files in parallel and reading entire blocks, right? But we'll see, well, exceptionally, we can actually make use of that in MapReduce. Parenthesis closed, we'll come back to that in a few weeks. So for now, we can forget about that. Okay, so we saw what there is in a name node. It's the file namespace, the mapping from files to blocks, and the mappings from the block IDs to the data nodes. We saw what there is on data nodes. It's basically the blocks associated with integer IDs stored on the local drive and monitoring that everything's okay, that the disk is not crashing. So now let's zoom out and look at how all of these machines communicate together, because they have, of course, to be orchestrated in a way that makes HDFS work, right? So how does this all work? Well, here I depicted, let me tell you who is involved. We have here the HDFS cluster. I have put the name node here, and only 2 data nodes. Of course, there's more than 2 in real life. There's more like hundreds of thousands, but I just put 2 in there. And then this is the client. This is whoever is uploading files and reading files from HDFS. So what's important here is that, of course, they will communicate together. These are these arrows here when they communicate together. But here there are special arrows that are a bit thicker, and this is the actual data. So you notice one thing here. The actual data is between the client and the data nodes, but there is no data in there. You never, ever see any actual data between the name node and the client or the name node and the data nodes. The name node couldn't care less about the data, right? It's just the data nodes that deal with it and that communicate with the clients. Okay, so This is just the same picture, but with the name of the protocol. So the name of the data when it flows is called the replication pipeline, and it will become very clear to you why it's called the replication pipeline. Then we have the data transfer protocol, which is for the data to flow between the client and the data nodes in both directions. The communication between data nodes and name node is called the data node protocol. And the communication between the client and the name node is called the client protocol, right? But let's go through them. Let's take it one by one, and I will now show to you. So let's start with the client protocol. So the client protocol is between the client and the name node, right? So what happens between the client and the name nodes? So the client and the name node communicate on a high level, right? It's like the C-level executives of a company drafting contracts, but they are not the ones who actually do the implementation. It's the computer scientists, right? So the metadata operations is something like, please create that directory, please delete that directory. I would like to upload a new file, please tell me how, or I would like to delete that file, and so on and so on. It's on the very high level operations. The name node, when this happens, will send back information to the clients to tell, for example, if the client requests to read a file, then the name node is going to answer, okay, you can read that file. And by the way, these are the block IDs and these are the locations of the blocks that you will find. And then you have to go to the data node to find them. All right. This can all work via Java, typically. And you can do it programmatically, but of course, you won't have to deal with that because there's libraries that do it for you. So I don't think we will even look at any Java code in this lecture. This is all nicely hidden. Okay, client protocol, is it all clear? All right, what's very important, there is no data transferred here. There are no blocks involved at that level. Second, the communication between the data nodes and the name node. The important thing in there is that every couple of seconds, the data node is connecting to the name node and sends what's called a heartbeat, basically a sign of life. It's like every 3 seconds, I'm still here. I'm still here. I'm still here. I'm still here. This is how it works. So basically, the data nodes, they keep connecting every couple of seconds just to say I'm still here. This is what happens. And of course, they do it, 1,000 data nodes all do that. So the name node receives a lot of these heartbeats. But since it has the heartbeats, then if suddenly one of the data nodes stops giving any sign of life, that there is no more heartbeat incoming, then the name node will start figuring out that there is a problem with the data node. And then it can mark it as down or crashed or whatever. And then it can basically make sure that if we consider that the blocks that are on that data nodes are lost, then it will replicate the other blocks to other data nodes to make sure that we are back to 3, right? So all the nodes that were on the crashed node, now there's only 2 replicas left on the other machines. So the name node is going to orchestrate things that we make new copies in order to make sure we are back to 3. We always want to be back to 3 replicas. For whom is that clear? Right. So this is what the heartbeats are for. It's for the name node to know if a data node suddenly stopped being responsive. So of course, there's other things that you can do. So the heartbeat is every 3 seconds. And every 6 hours, there is a bit of paperwork. So every 6 hours, the data node sends a full report, everything. These are all the blocks I have. These are the sizes. These are the hashes, and so on and so on. So it's a full block report every 6 hours. There's also some registration paperwork. So when a new data node is added to the cluster, it's very dynamic. You can do it in real time. So you just install new machines, then connect them to the cluster, and then they will register to the name node saying, hello, I'm new. I'm a new data node. Please add me to your system, and then I will kindly store blocks, right? So this is registration. And block received is just an acknowledgement that say, hey, some client sent me a block, and this is the ID, and now you should know that I have it, right? The name node is also able to give instructions to the data nodes, right? So it can instruct a data node to create a copy of a block. If it notices that a block is replicated only twice, then it can instruct another data node to make a copy of that and store a 3rd copy. This is a block operation. Now, what's very important is that these instructions that the name node gives to the data node, they are always as a reaction to a heartbeat. The name node will never directly connect to a date node. It waits for 3 seconds, it waits for the next heartbeat, and as soon as it receives the heartbeat, hey, I'm still here. Oh, by the way, here is an instruction for you. This is how it works. Okay, so this is the data node protocol. And finally, this is the actual action. This is the actual data that gets transferred, but you see there is no name node here. It's all between the clients and the data nodes. So what happens when the client wants to read data, let's say you want to read data or write data. So when the client wants to read data, so as you remember, when it wants to read data, it received the locations of the blocks and block IDs from the name node, and then it connects to the name node. Oh, what's going on? Oh. And the data flows here. So the data node is going to send the actual data, this is the actual bits of the blocks, over the network to the client. And it works the other way around, right? So the client can upload files to HDFS, and then it will connect to the data nodes to upload these blocks. But when it writes, something additional happens. When it writes, we need to make 3 copies, right? Whenever you upload something to HDFS, you need to make copies. This is done with the replication pipeline. What's going on is that the name node will say, for this new block, please store it on this data node, this data node, this data node. And what's going to happen is that a pipeline is established, meaning a connection like this that flows through the data node in sequence. And then you ship over the block. That data node will ship it over to the second data node that will ship it over to the third data node. This is called the replication pipeline. So as soon as you upload a new block into the system, you set up a replication pipeline to already immediately store it in 3 different copies. For whom is that clear? All right, so for reading, you only need to connect to 1 data node. And for writing, you connect to 1 data node, but then there is this pipeline behind with more data nodes involved. Do we have a question? Yes?
How does the data node decide which data nodes to contact?
Oh, it doesn't decide. This is decided by the name nodes. So basically, I will show you, I have an animation for that. When you want to upload a new file, you have to connect to the name node and ask or tell about your intention to upload a new file. And then the name node will answer, okay, yes, you can create your new file. Here is the first block for you, and I ask you to store it at this, and that data node. So here, at that point, you receive 3 addresses of data nodes. And then what happens is that the client connects to the first one of the data nodes and tells the data node about the other 2, right? It says, oh, by the way, you need to also inform this and that data node about the blocks. And then it's the job of the first data nodes to connect to the other 2. But the decision of why these are these data nodes was made by the name node.
Yep, but how's it made, the decision?
Oh, that's a very good decision, and I have slides for that. There's a strategy. So basically, first you want to spread the data over the cluster, right? So you want to make sure that if there are nodes that have less data, then probably you want to prioritize them for adding new blocks. Another aspect is that you know the structure in the data center, you have the nodes that are piled up in racks, right? And then you have multiple racks. When there is a crash in the data center, it has a tendency to be localized, meaning that if there is a crash on one machine, there's a higher likelihood that there's going to be a crash on other machines in the same rack, for example, if there's a network switch. So because of that, you need to be aware that the blocks are not only distributed across machines, but they are also distributed across racks. Because if you have the 3 replicas in the same rack, that's not a good thing. Right? If the rack crashes, then you lost all the 3. So there are strategies for that, and I will come back to it. I don't know if we'll have enough. No, I think we'll have enough time today, but I'll come back to the strategy and more details. Yeah.
Thank you.
Yeah, thank you. All right. Other questions? Nobody on Zoom? Okay. All right. Now, this metadata I told you about, so it was here, right? I told you metadata here. So what can we do? We can create directories, we can delete directories, we can write a new file, we can append to a file, meaning it already exists and we just append at the end of the file, new data. We can read files, we can delete files. That shouldn't really surprise you, right? This you can do on your laptop too. But it's pretty much the same way that it works. I mean, it's a file system, it has a hierarchy of directories and files, so it works pretty much in the same way. The look and feel is the same, but there is one thing that's different. It's going to be slow. Slower than what you have on your laptop. That's the main difference. Okay, now I have this animation that I want to show you. This is putting everything together that we've learned into a big animation that now shows the actual order of things that are happening. So you know everything already. I'm just putting it in sequence. That's all I'm doing here. So imagine that this client on the left wants to read a file. To which machine does it connect? The name node, yes, it connects to the name node. Very good. So it says, okay, it asks for the file. I would like to read this file. So it asks for the file. So the name node says, okay, fine, you can read that file. It checks for access control and so on, you authorize. And then it ships the block locations. So it basically says, these are the block identifiers. This is the data nodes that have a copy of it. So probably 3 data nodes for each identifier. And it even has the luxury that the name node will give you these 3 data nodes for each block sorted by distance to the clients. How cool is that, right? What do I mean by distance? I mean physical distance. You are in the data center, you have the racks. If you are in the same rack, the distance is shorter. If it's in a different rack, then the distance is larger, right? So it basically sorts by distance to the client. The first data node that is listed is the closest one, and then another one a bit further, and then another one a bit further. But now you should be wondering, what does it mean, the distance with the client? Because the client, you might think that's your laptop, right? Your laptop is not in the data center, right? So what does it mean, the distance between your clients or your laptop and the data center? Well, in practice, the clients that connects to HDFS is not going to be your laptop. That's going to be clear when we use MapReduce and Spark. The client that connects to HDFS is actually another machine in the same cluster, right? In fact, every single machine in the cluster can be a client connecting to HDFS. So this is why it makes sense. If you consider that all of these nodes here, they are all in the data center, right? So keeps this is in the data center, this is in the data center, this is in the data center, and this is also one of the nodes in the data center. Then the fact that you sort the data nodes by distance, so maybe this one which is closer than this one, physically, and then it tells you which ones you should try first. Because of course, if you're the client, you want to try first those that are close to you, right? Because there's less distance, so it's going to be faster, there's going to be less latency. Okay. It's like when you want to do shopping, right? You go to the grocery stores near you. You don't go to the other side of the country in order to shop, right? So it's exactly the same thing here. You basically connect first to the data nodes that are physically close to you. All right. And then what happens is that the client is going to take, for the first block, is going to look at the 3 data nodes that have a copy. And then what happens is what I showed you here. Remember, this replication pipeline. So it's connecting to the closest one of the 3, the first one in the list, closest one of the 3, giving the information about the other 2 data nodes that must be involved, but it's the job of the data nodes to create the pipeline, all right? And then this is how you basically have this, this whole thing in place. Now, why did I put this input stream and thing here? The idea is that if you actually, you as a human, use Java or a Java library or you know, the command line to connect to HDFS, you will not even notice this whole thing. You will not even notice the data nodes. It will just feel like incoming bits, just like you would on your local file system. So basically, what I'm saying is that the complexity of connecting to these 3 machines, so this complexity right here, is hidden from somebody who is reading from the command line. So if you try to read the file from the command line, all you see is incoming bits. The complexity of connecting with the pipeline and so on is all hidden from you, right? But of course, you know about it because I told you that there is in fact this pipeline right there, but this is all hidden. Okay. So this is for reading a file, right? So basically you do this for one block, then you receive a block, then you do it for another block, then you receive a block, then you do it for another block, then you receive a block, and so on and so on and so on. Yes? in the same data center. So typically, when you have, so the question is, where are the data nodes located that have the blocks? They are in the same data center. A typical setup of HDFS is in one data center, in one room, you have 1,000 machines, and these are the nodes of your HDFS cluster. That's a typical setup, right? There also exist technologies that go beyond the data center. Google has one, in fact, that has some even bigger system involving thousands of data centers. So then you basically have not only you not only have the name node in that case, you actually have the name node in each data center, and then you have what they call a universe master or something, right? So this is basically a node that's responsible for the whole world, the thousands of data centers all over the place. But this is not what we are doing today. In what we are doing today, you have to imagine a single data center, for example, here in the north of Zurich, a single room with 1,000 machines in there, and these are all the machines. Absolutely, absolutely. And in fact, that happens when the data center catches fire, and there are real life examples of that. If you have not backed up your data to other locations and other data centers, then you lose everything. Right. So you always need to keep that in mind, especially when you have a company and the data is crucial for the company, then you need to always copy the data. And in fact, this is probably the reason why these bigger systems were invented that are even able to go across data centers. Right. S3 is also across the whole world. Right. So S3, blob storage, and so on, they really replicate across locations. Okay. All right. Something I forgot to say is here we are reading a file, not writing, right? So when you read a file, you don't actually need to read it from all the 3 locations, right? You just read it from once. So it's whoever has it first, right? You first try the closer one, then the other one, and then if there's still no block, then the third one, right? Okay, so this is reading a file. Now I have an animation for writing to a file. So if you write to a file, then we say that we want to create the file, we get back an acknowledgement saying, okay, here's your first block ID, and here are the 3 locations that I would like you to store your block at. Then you connect to the first data node, you let it organize the pipeline, giving the addresses of those that you want, and then you send the data over. Now, what's happening here is complex. This is basically network stuff that only computer scientists can make sense of. But basically, all that means here, it's basically highly optimized. You basically just keep shipping data over the network without waiting for an answer, and then you get your confirmations at the end, right? That's pretty much what's going on. It's not very important that you understand what's going on here, right? The only important thing is that you understand that basically the data is flowing all the way like this, and then at the end, you get an acknowledgement. Act means as acknowledgements, confirmation that it's been received. And then you do that, and then you do this. You have the second block, and then you write the blocks in the pipeline, and then you send the data, and then you have the acknowledgements. That was your second block. Then you go ahead with the third, fourth, fifth. So block by block, you just iterate. Just keep iterating and iterating and iterating and iterating and iterating and iterating. And at some point, you're done. You have uploaded all of your data. Then you connect to the name node to say, okay, I'm done. I have uploaded all of my data for that file. Now you can release the lock. What does that mean? Now people can read it. Because when you're not done uploading, nobody can read it yet, right? But once you're done uploading your file, you can say, okay, now I'm releasing the lock. Everybody can now have access to the file that I have just uploaded. All right. Then the data node says, okay, now I need to just do a few checks. So it checks for minimal replication. So at that point, by default, it only checks that each block is stored at least once, not 3 yet, just once. That's at that point, the minimal replication. If it has a confirmation by the data nodes that we have 1 copy of each block, then it acknowledges to the client that this is all done. However, it's not done yet because in the background, later, it will make sure to bring it up to 3. But if you already have a copy, then making copies can be done later. You don't need to make the client wait for that, right? So the copies and making sure that we are at 3 copies per block can be done in the background. And it's at all times, because if there are crashes, if the data nodes crash, then you're back to 2, and then you again need to make new copies to bring it back to 3. Okay. Now I'm coming to your question. How do we store the replicas? Well, first, this value of 3 is actually a default, but you can change it. If you're not happy with 3 replicas, you can make it 2, you can make it 5, you can make it 10 if it's really important data, but you can specify that. But default is 3. Now, what we need to consider for that is the distribution of the block, to not overload the network and so on. And for this, you need to understand that in the data center, the nodes are organized in racks, right? These towers. So there's somehow a topology of the machines in the data center, right? We have first the cluster, the entire room, then we have 1 rack and 2 racks, and then within a rack, we have nodes. Now, you need to understand that if I have 2 nodes A and B in the same rack, then they are close to each other, right? So in that case, I'm saying there's a distance of 2 because there's 2 edges in the middle, right? There's one that goes from here to here and then here to here. So the length of the path between A and B is 2. If they are in different racks, then 1, 2, 3, 4, right? So then the distance is higher. This is what I meant earlier in terms of distance, right? Now, here's the strategy. When the client, which is one of the machines in the data center, typically connects and wants to create a new file and upload blocks, the first replica of the block is going to be on the exact same machine, because the client might also itself be one of the data nodes, right? It might be the same machine. So if that is the case, you just make a local copy. The first block will be exactly on the same machine as the client. That's going to be super efficient. You don't even need to go over the network for that, right? Okay, so same node as clients. The second replica will be in a different rack. We want to be somewhere else in the data center in case the rack crashes. And the third replica is another node in that other same rack. So not the rack of the clients, the other rack. So you basically have, if the client is here on the right, you have a copy of a first copy of the block on the client, and 2 other copies on 2 nodes in the same different rack. Okay, does that make sense? All right, and it's a compromise because you could say, okay, why not a third rack, right? But if you have a third rack, you overload the network, right? Because then you use the network wires even more in order to go to yet another rack. So this is a compromise that we do here. Then you could say, okay, why not the 2 replicas? Why is the second replica not in the same rack as the client? This is why. Because if you store the second replicas in the same rack as the client, you're going to end up with a concentration of blocks on the same rack. This is dangerous. This sounds like if there's a crash, something goes wrong, then you don't lose 1 block, you lose 2. You don't lose 1 replica, you lose 2 replicas. Then you're left with just 1. So that's the reason why we prefer this. So for the yellow block, it's on the client and on that rack on the left. The green block is on the client and on a different rack on the right, and so on and so on and so on. That's how it works, right? So far, so good? So that's the strategy to spread the replicas over the data center. And this is all done by the name node, because the name node is aware of how the data center works. All right, now, there is a problem with that system. The problem is that if the name node fails, well, we have a problem, right? Because the name node is the one that knows about the hierarchy and the files and the blocks. So if we lose the name node, we lose everything. There is nothing we can do with the data of the blocks if we don't know how to assemble them. It's as if you would buy some piece of furniture from IKEA and be left with the parts, but you don't have the manual to actually build it, right? So this is pretty much the same. So what if it fails? Well, we need to proactively make sure that we have some plan if it fails. And the plan is we do a backup, but we only do a backup of the namespace and the mappings, 1 and 2. We do not back up the locations of the blocks. Why don't we back up the locations of the blocks? Because that we can recover from the heartbeats, right? If you fail, all you need to do is wait for the data nodes to connect back to you, and they will tell you which blocks they have. So that's why we don't care about 3. So that we don't have to back up this part. We need to back up the file namespace, and we need to back up the mapping from the file names to the blocks. How do we do that? Well, we just store somewhere on some persistent storage. It's going to be some network drive or network attached drive somewhere, not HDFS, of course, because otherwise you have a bootstrap problem, but it's not HDFS. It's stored on some drive over the network That's called the namespace file. It's a backup of that. It's a snapshot at a specific point in time of all of that, and then we can recover it if needed. All right? I think you deserve a break. We deserve a break. Shall we take a break? All right. So let's have 15 minutes of break. I'm almost done actually with HDFS. So after the break, I'll finish and then we'll start syntax. So I will see you at 15. It's 9, right? So 15 past 9.